So in this tutorial, we're going to look at a couple different distillation blocks within Pro2 and apply to this distillation example. So we want to separate 225 metric tons per hour of an equal molar mixture of benzene, toluene, ethylbenzene, orthoxylene, paraxylene. Our feed is going to be saturated at 330 kilopascals, and some constraints that we have is that toluene needs to be recovered in the distillate above 99%, and ethylbenzene needs to be recovered in the bottoms above 99%. So I'm going to open up Pro2. As a reminder, if you have any questions or is not sure where something is or what or how to solve something, you can go to this Pro2 documentation here, and that will bring up this with all of these links. But we want to open up Pro2 Simulator. So first off, we see that these are red, so we need data for these. So our component list is going to be most commonly used, and we have benzene, toluene, ethylbenzene. Now, anything that is para, meta, or ortho, you if you type in ortho, it's not going to work. So you need to type in O, and then it will pop up. Same with para. So we have our 5 components. So we're good with our component selection. Now for the thermo, we can choose, of course, any of these, but we want actually to go back to our figures for the thermo packages. So we can see, starting off, so the ortho and meta, they will have some polarity. They are non-electrolytes. So if we go to our figure 2, if we have polar non-electrolytes, our pressure is going to be less than 10 bar. We're going to carry out this distillation at atmospheric pressure, or near about. Now, if we do or do not have interaction parameters in liquid-liquid, we can stick with NRTL or UNIQUAC or UNIFAC in our liquid-liquid equilibrium. We do have some interaction parameters within Pro2, so we're just going to stick with NRTL or UNIQUAC. So, UNIQUAC, single phase only. Now we have our environment set up, we can add our blocks. So the shortcut method should not be used as a final distillation column, but it can provide some very useful information. So if we have our shortcut block, our inlet and outlet, and I'm going to call this stream shortcut distillation, or rather, there. We'll keep it as distillation and have this one be shortcut bottoms. So in our feed stream, again, we have a total fluid flow 225 tons per hour. So 225 tons per hour. We can change our units of measure here because it default to pound moles per hour the way it's set up right now. So I'm just going to stick with kilograms per hour. 225, so 225,000 kilograms an hour. Now our mole composition, if it's equal molar, then all of these are going to be 0.2. Looking good. So now we can specify our thermal condition. Now it was specified for us already. It's a saturated liquid at 330 kilopascals. So if our first specification is pressure, we want to change this to kilopascals, let Pro2 do all the conversion for us, and we're at our bubble point. So we're good to go on the feed. Now our shortcut, we need to specify some things. So our specification. Now here, we actually have these given to us in this case, or we have certain constraints or requirements that we need to adhere to. So our toluene recovery in the distillate should be 99%. So that could be 99% of 225 tons per hour needs to come out. But if we specify a lower mass yield or a lower yield, then our material and energy balances might agree a little bit faster or a little bit more, fewer iterations. So we're actually going to specify that the toluene recovery in the bottoms should be no more than 1%. So we have stream bottoms, and we have a flow rate of a specific component, that being toluene, and we want to specify that in kilogram per hour. And 1% of 225,000 kilograms per hour is 2,250. So our second parameter, we want to specify the opposite. So that would be ethylbenzene recovery, and the bottom should be greater than 99%. We're going to specify that the ethylbenzene recovery should be less than 1% in the top. So a flow rate of a specific component, ethylbenzene, specify kilogram per hour. Okay, and our value again is 1%, so 2,250. And we're good. But now we need to specify some product. So in the distillate, say we just have an initial estimate of 100,000 kilogram per hour. Change our units of measure, make sure that everything lines up. 100,000 kilogram per hour. So, ready to go. Click run. So now that we have our shortcut column, and our Finsky index is 9.6, we can now look at proper distillation column. So the theoretical number of trays is 9.6, rounds up to 10. Our number of theoretical stages, let's just say, is 20. So we'll have twice as many as we absolutely need. So we can add in our stream, feed stream, and our liquid distillate, and our product stream. So I'm going to call this distillation column distillate, and distillation column bottoms. Again, in our feed stream, we have a pressure of 330 kilopascals. So we can change our units of measure so we don't have to convert in our head, 330 kilopascals. And our specification for temperature is bubble point, saturated. Oops. But we need to specify our flow rate composition. So again, we have 225 metric tons per hour. We're going to keep that in kilograms. So kilograms per hour is 225,000 kilograms. So equimolar concentration, 5 streams. So 0.2, make sure that our total is 1. And we're good to go on that. So now we have to look at the column itself. So our pressure profile. You can just say that our top tray pressure, or coming out, we have atmospheric. Now I'm making this up right now. This can be anything, pretty much below 330 kilopascals. So our feeds and our products. Now Now we want to specify, we have feed tray anywhere between 1 and 20. But before we do that, because these are lighting up, these actually are tied to our performance specifications. So we're going to skip the feed tray for the moment and look at our performance specifications, because our constraints already are that our toluene recovery in the distillate should be greater than 99%, and our ethyl benzene recovery in our bottom should be 99%. Now we're going to switch those, just like we did with the shortcut column, and say that our toluene recovery in the bottoms should be no more than 1%, and our ethyl benzene recovery in the distillate should be no more than 1%. So those will become our specifications. So with the column, you would typically, or you could use the reflux as a specification, but we're not going to do that. So our parameter for the first one is going to be our distillate. We can specify a flow rate of a selected component of ethyl benzene. We want to specify this in kilogram per hour. And we have ethyl benzene in the distillate no more than 1% of our flow. So 1% of 225 metric tons is 2,250 kilograms per hour. And in our second specification, we're going to specify in the bottoms that we have a specific flow rate of toluene. Again, in kilogram per hour, and that value is 1% of total flow also, so 2,250 kilogram per hour. So our specifications are okay, so let's go back and look at the feeds and products. So if we have 20 trays, let's try feeding on tray 10. We can say that maybe initial estimate, we have about a little less than half of our product coming out the distillate. So 100,000 kilograms per hour. Again, this is just a guess for now. So we're good to go, no more red, and we can run it. So we have two little warnings, but again, a warning is not that bad. Now, if we had an error, then of course we couldn't use any of this information in the column to properly size anything. So let's have a stream table pop out, and we want to specify, or we want to see how our shortcut and our distillation column, distillates and bottoms, look in terms of our component weight rates. So that will give us pounds per hour. And because we specified everything in kilograms, I'm actually going to go back and change the units of measure to SI. So here we have our kilograms, and this as solved. So we have our distillation column bottoms. We have toluene is 2,250 kilograms per hour. So that is the first or second specification, and the first one they specified was actually that we have in the distillate of the distillation column, we have ethyl benzene 2,250. So everything has worked out for our specifications, and we know that because, again, so now that we have a column, it's actually not optimized yet. We have 86.5 million kilojoules per hour as our reboiler duty, and that can cause a lot of prices to increase. So actually, we come over here to utilities, and we select an optimizer. We can then optimize maybe where the feed tray is, or any other parameter that you want, or variable. So if we want to have an objective function of the reboiler, we have a column T1, that's our distillation column here, and our parameter is the reboiler heat duty. And we want to minimize that by changing our feed tray, let's say. So tray location, the feed. And that turns out to be S2, just to make sure that it's not S1, that we chose the right column. Now we had 20 trays, so our minimum value is 1, and our maximum value is 20. So now if we run this again, we can see that our optimizer is blue, it's solved. We have the same values or the same specifications on our outputs for our distillation column, and we can look at these results and see that our initial value is 1 and our optimal value is 8. Oh, sorry, 10. Our initial value is 10 and our optimal value is 8. So we can go back and look at our distillation column and change our feed tray to 8. Run it again, double check the optimization, double check the results. So our initial value is 8, this is our feed tray, and our optimum value is actually 8. So you have a minimum reboiler heat duty. So the Fensky index can tell you your optimum or your minimum number of trays. In this case, it'll be 10. And the Underwood method, which is actually what we just did to try to minimize or find our optimal feed tray location, is called the Underwood method.